Hello, and welcome to your least favorite video lecture of all time. This is Shear, the infamous Shear, in pre-stressed concrete. Excuse me. I had done what I thought was a very nice video and covered all this stuff, and since it's miserable, I didn't really look forward to doing it again. But ACI 318 released ACI 318.19, and in that code, they just decided that all of these sixes, they used to be eights, all the eights needed to be changed to sixes. So I think they just love to mess with those of us who try to teach other people how to do this. So this is this is the change. So brand new lecture, 2024, 318.19 code. So here we go. And I apologize ahead of time. You're not going to enjoy this. Nobody enjoys this. It doesn't make much sense. Little background on this is that if you remember with the FPS equation, the pretensioners had their own FPS equation, and it was long and complicated, had variables in it that didn't seem like they could possibly affect the actual ultimate strength of a pre-stressing tendon. But they threw everything in there. I mean, every variable you could come up with that was in their test made it into their equation. And the post-tensioners came along. You know, and I'll back up. The pre-tensioners, and I really believe this, don't want you doing their work. So they want to make it as complicated as possible. They don't want it to be easily done by hand, so you have to own software that can do this. The post-tensioners, on the other hand, came along, and in my opinion, took a much more complicated type of system, an unbonded, undulating tendon running usually through multiple spans, and made a much simpler equation for FPS, somehow, some way. So you'd think when they came to shear, they would do the same thing. And I am again of the opinion that the pretensioners created some design equations for their shear design, you know, relatively simple, almost always simply supported, often just straight flat tendons. Worst case, maybe a harp in there, but a simple system. And they came up with about the most complicated equations and methods for designing shear that you could come up with. And you would think that the post-tensioners would do what they did for the FPS equations and come along and do a much easier type of shear type approach. But they didn't. They lost the steam. They dropped the ball. I'm not sure what happened. And we're talking about back in the 60s, which creates another problem, is that all the people who were involved with these equations are gone. They're no longer with us. So, and I think they took their data with them. So really nobody knows what to do with these equations. You'll see, I'll point out a few things as we go. So anyway, that's the background. The post-tensioners just decided to adopt what the pre-tensioners had done for shear, even though I am going to demonstrate, or you're going to actually demonstrate in the homework assignment, that it really doesn't make any sense to have done that. We don't have simply supported members. We have continuous members, and our inflection points or our zero moments are not at the supports. They're at inflection points away from the supports, and all those things are going to cause problems. But nobody's cared enough to change it. There was some steam built up to make changes. I don't know if I get any credit, but I'd made enough of a stink, and we published a paper, my dad and I, which is at the end of this lecture. We tried to explain the problems, and ACI seemed to want to take this up and do something with it. But unfortunately, infighting happened, egos got involved. What was proposed was more complicated than what we already had. And eventually the ball just got dropped again. Nobody wants to do the fighting. So here we are. And probably for the rest of my career, these will be the equations used for beams. This is beam shear for the design. Okay, with that fun introduction, I know you're excited. Let's get going. The code says that you have the option of using what they call VC. Now, to me, it was confusing to call the equation VC because if you read the way it's written, all of these equations we're going to present are ultimately VC. So my dad started it with the PT data manual that he created, his notes and my notes. We added an N to it. So we're going to call this VCN. It doesn't appear that way in the code, but it differentiates from the equations. You're going to see the VCI and the VCW. So they all get their own little subscript, so we know what we're talking about. And the end result is that whatever we decide to use out of all those will be what we plug in for VC here. So what we're trying to do is figure out what the concrete component of the shear strength is. Remember, everything you did in reinforced concrete, we have a nominal capacity for shear. It's comprised of a concrete component and a stirrup component. We add those together and call that the capacity for shear. Same thing here. Nothing's changed about that. What's changed is in reinforced concrete, we have a really simple 2 square root F prime C BWD equation. And I'll show you what we have in pre-stressed concrete. Not nearly as fun, easy to use, or straightforward. So here's the first equation. And you are allowed by the code to just use this equation. They call it the simplified one now, I think. I mean, you can run forward and just use this and not do the other two that are coming. But since you're using computer software, you're not going to do that. The computer software is going to run through all the calculations for all the equations and come up with the best one, best being least amount of stirrups and most economical, and that's what we will use. Sorry about that. Work keeps getting in the way. Okay, looks like I'm continuing. So the VCN equation, we only have to use this one. And what does it look like? Well, here it is. We start off with some amount of square root F prime C. Why 0.6, nobody knows. Then we add 700 times these values. Now the first thing that jumps out at me when I see this equation, and this is specific to pre-stressed concrete, is that there's not a single thing, in my opinion, in this equation that has anything to do with pre-stressed concrete. There is a depth to the pre-stressing, which is really just another D, but that's it. What this equation actually has to do with pre-stressing is anybody's guess. But it's in the code, so we're going to go with it. And by the way, there's not going to be logic or reason or epiphanies or a greater spiritual level that you'll attain by doing and learning shear. Now, there might have been in some of the other things we've talked about. There's some pretty cool stuff in post-tension concrete. Not here, not in shear. So you're just going to plug and chug and do what the code says without trying to find any deeper meaning. And that's the best way to approach this. And because they say so, this term cannot be taken greater than 1. So I guess if it's calculated to be greater than 1, we would put in 1. Okay? Yeah, nobody knows why, these are the things we do. Another interesting thing here, and there's a lot of history and guessing that goes along to why this happened. This DP has no limit, has no 0.8H lower limit, whereas every other DP in the equations we're going to see and every other D has that stipulation. Many people believe it was just an oversight. Somebody forgot to type that in there. But again, since nobody's around anymore to go back to and talk to about this, we won't know. But this DP will be the only one in the 3 equations we're going to spend time with that is just actually DP regardless of what DP is. Not limited to 0.8H. This D is limited to 0.8H. This is fun. It's fun to try to explain this stuff. Okay, again, Dad started this. I've continued it. We just added the N to the VC equation in the code. F prime C, always remember that whenever in any ACI equation, any one of them in any chapter, if it's under the radical, it's under the square root, that has to be in PSI. So don't make that mistake. Students make that mistake all the time. Don't stick 4 in there for 4,000 PSI concrete. Your results will be very strange. DP, distance to the centroid of the pre-stressing reinforcement. D, and this is where it gets a little confusing. D is defined, remember these are all ACI definitions, they're not Dirk Bondy definitions. This comes from the code. Distance from the extreme fiber and compression. D is, by the way, always measured. Any D anywhere in the code is measured starting from the compression face of the concrete to whatever they're talking about. So that's always the starting point. No different here. We start from the extreme fiber and compression, and we're measuring, this says, to the centroid of all tension reinforcing. Sounds easy, but what does that really mean? Nobody actually knows the answer to this either. Is it the geometric centroid of the rebar and the post-tensioning steel? Is it the force centroid? Because remember, the post-tensioning is 270 KSI rupture strength. Yield strength of rebar is 60 KSI. Do we average those? What do we do to get D? Well, the answer actually is in all software that I'm aware of, our software, all design examples, D is just the distance to the pre-stressing. The pre-stressing will always be inside of the rebar. The rebar will be at the top of the beam and the bottom of the beam. Same thing in slabs. And the post-tensioning will drape up to, sometimes meet it, really never should go beyond it, top or bottom, and will typically be somewhere less inside. So it is conservative to take D as just the distance to the pre-stressing steel. And that's what we're going to do. This is conservative, and it's the only thing that actually seems to make sense. So you could stop there. That could be your VCN equation. You can just use that, but we're not going to. Computer programs won't. There's a next equation. There are 2 more equations, and what ACI says is that you can use the smaller of these next 2 equations if you'd like. The smaller. So this VC, all these equations are VC something. VCI, apparently the I stands for some inclined cracking. So they noticed inclined cracking, came up with one equation to explain that shear. That's at least how the story goes. And this is the VCI equation. This is the miserable one. This is the one that really makes all of this shear stuff so complicated. And within that, this one term, this effective cracking moment, contributes the most confusion. So there we go. Another thing to point out, remember, these are capacities. We're just looking for the shear capacity of the concrete only, just the concrete. We're trying to say how strong at this location is the shear in concrete. For some reason, the dead load shear at that location is a term that just simply gets added to what the capacity of the concrete in shear is. I'd love for somebody to explain that to me. How the demand, how the dead, not the live, not any other shear, but the dead load shear is actually additive to what the concrete strength is. The strength and the load, usually you calculate the strength that you have, you check it against the load that you have, and you see if you have more strength than load. But this is actually a component of the strength. You can't write this stuff. Okay, so Now there's some stuff in the code where dP need not be taken in this equation, less than 0.8h. Like I said, the last equation, that VCN equation, is the only time there's no limit. The dP is just dP. From here on out, in this equation, dP and d will be limited. You don't have to take them less than 0.8h. VCI is also, and this just seems to get more complicated in the code, need not be taken less than 2 square root f prime c, but there's another caveat in there that says under these conditions it's 1.7 square root f prime c, which is actually, that 1.7 has always been there. The 2 square root f prime c just got added sometime recently, but it doesn't make sense to ever be less than 2 square root f prime c because you always have the option not to use the pre-stressing equations. The pre-stressing equations give you a better value of shear capacity, of VC. You can always revert back and not use those. Just use reinforced concrete shear at 2 square root f prime c. So why there would ever be a lower limit that was less than what you can just default to doesn't make sense and hasn't. But so anyway, we will use the lower limit of 2 square root f prime c, mainly because you can always go back to that. Okay. So this is the messy thing. Effective cracking moment. This equation is trying to figure out at what moment you can expect cracking in the beam. Remember, this is the VCI equation, and it was based upon them seeing inclined cracks in the beam. So need to know when it's going to crack. Okay. Be careful. In the code, this is just written as YT. But I have been using the term YT to describe the distance between the elastic centroid of the section to the top of the beam, and YB is the dimension to the bottom of the beam from the elastic centroid. So I don't want to use that term. That would confuse you. It looks like it's always Y to the top in the way we've been doing this. So I've spelled out the word tension, which is what the T means actually in this equation. So, and then if you realize this is just the section modulus to the tension side. So why the code felt the need to write the moment of inertia divided by y to the tension. I had not just put section modulus in. Again, something we'll never know. And by the way, back in the 60s when this was developed, the allowable stress for pre-stressed concrete was 6 square root f prime c. Eventually it occurred to somebody that the cracking stress of concrete is not 6 square root f prime c, it's 7.5 square root f prime c. So the allowable stresses got changed to 7.5 square root f prime c. But these equations that have just been baked in didn't get changed. So this, there's a solid argument that this should have been bumped up to 7.5 square root f prime c if you're following the logic of trying to figure out what the cracking moment is. But it didn't happen. Everybody's afraid of these equations, so they just leave them alone. Fine. 6 square root f prime c. FPE is defined as the compressive stress in the concrete due to the effective pre-stresses forces only. So just the compressive stress due to pre-stressing where tensile stress is caused by externally applied loads. So to understand this, what they're saying is that externally applied loads are going to create tension. We're trying to figure out with that tension when this beam is going to crack. But pre-stressing offsets that. So remember, if the applied loads are creating tension on one face of the beam, if we've laid out post-tensioning or pre-stressing that makes any sense at all, it's the opposite is happening. So there should be pre-stressing compression happening at that location. Pre-stressing compression happens due to the P over A, just the direct compressive force, plus the M over S value. So the M over S value will be use the section modulus also to the tension face, but due to the pre-stressing we'll expect compression. Now another thing that can get complicated is I've been using a sign convention that says that pre-compression is negative. You have to be very careful when we go to the code. The code is always done in absolute values. The code will put in the signs that it wants. It's not looking for you to put any signs on anything. So, and this is true to the best of my knowledge throughout all ACI equations. You calculate a number and it's an absolute value number. The code will then put in the signs that it feels are appropriate. So when we calculate this, our F over A is not the negative F over A that we've been using up till now. It's just going to be a positive number, and we're going to add it to a compressive stress that's another positive number that's going to go in here. So hopefully that is not a confusing thing. And we're going to subtract out the dead load stress. So basically the idea here is we've got a cracking stress. We've got some compression that we'd have to overcome. So we have to get to the cracking stress to crack. We have to overcome the pre-compression of the pre-stressing. But then we're penalized by whatever the dead load stress is that was there. So you kind of understand this. It makes some sense. Okay, and if we back up, then we've got a couple other terms in here that add to the confusion. There's a VI and an M max that are placed in front of this effective cracking moment. So let's look at that for a second. VI is defined as the factored shear at the section due to externally applied loads after the member was pre-stressed. So it's just the loads applied after the member is pre-stressed. So it's not going to include the initial concrete dead load. But then that additional load, whatever happened from that point on, gets factored, and the live load gets factored with it. So why would they do that, you ask? The answer is these beams were built in a shop somewhere by a precaster, provided to the university who ran these tests. So the dead load was already in there, the weight of the beam itself, before they started the test, and the pre-stressing was already there. So their tests only included the load from that point forward. So that's how these equations got written. It's a true story. So that's a very complicated thing to actually have to figure out, particularly when we get to post-tension concrete and when we add the complication of the fact that we have columns up above that are not there typically during the construction process, when the initial dead load is applied and when the pre-stressing is applied. Then that upper column is built later and the live load comes along and any additional dead load. So this can get complicated. You can have two different stiffness matrices that you're talking about based on whether or not you have a column or not for some of this loading. We've got a simpler way that we're going to approach this, and it works just fine. But I just want to show you the fun that the code was written under. Okay, so that will explain the VCI equation. Maybe it'll get clearer when we do the example, maybe not. And then the other equation that we get to compare the VCI equation to and take the smaller of is the VCW equation. This is the only equation that actually makes sense to me, if you want to know the truth. When my dad and I wrote a paper, we basically started with this format, this idea, not the same numbers, but what made sense was to start at some value of square root f prime c. Now, I think eventually we proposed just starting at 2 square root f prime c, because everybody agrees that non-pre-stressed concrete has that, and then we added something for the pre-stressing. Seems to make logical sense. That's what this equation does. I don't know why, but they start at the 3.5 square root f prime c, and then add 30% of the direct pre-compression. The FPC, compressive stress in the concrete after losses at the centroid of the section. So just F over A. What is the average compression in the member? Makes sense. It makes sense that when you look at a beam, that squeezing it would increase the shear capacity. I hope that makes sense to you. The aggregate interlock, the 45-degree shear that's grinding against each other, if it's under compression, it should be harder to shear that beam. So just a gut level impression of that. it kind of makes sense. So that's what this equation says. It just says you've got direct compression. You're going to take 30% of that, add it to somehow the number we started with, multiply by BWD, and you're going to get a capacity. Now, what is this? VP is the vertical component of pre-stressing. So if we have a precast beam, which is the one they based this off of, and maybe they were draping. The precasters, this is going to be the most elaborate type of draping that they're going to do. The vertical component's pretty easy to calculate if your tendons are straight like this, and then that would be a constant number for the duration of this portion. Okay for them. For us, we've got a whole different situation. And our beam is going to be continuous. We're going to have let's say something like that. So, we're going to have low, high, low, back to mid. So our vertical component is constantly changing. The tangent of this is constantly changing. You wouldn't want to rely on that because those are your calculations, but is it going to be built exactly that way? You don't know. And as you get close to the support, you're going to get a larger gradient. You're going to get smaller gradients. You're going to actually get little gradient right at the support. So this thing gets complicated, and it clearly wasn't meant for us. So every software program, every example ignores that term. It just says we're not going to take advantage. We'll be conservative, and we will not take advantage of whatever the vertical component of the pre-stressing happens to be. Okay, so the equation actually makes some sense. It actually has something to do with pre-stressing, amazingly. Okay. This is where I got myself in trouble for the first edition of the book that I wrote. And I still stand by this, but I've been hammered down by everybody else. Apparently, I think Brian and I are the only ones that read the code this way. But the code says VC shall be less than or equal to 5 square root of prime C. And if you read the code closely, what it says is that all of these three equations can be used as VC. So VC can be the first equation. You can use this as VC, because remember, you're going up to this. You're plugging it in there. The smaller of VCI or VCW can be VC. It's your choice. Well, it's your choice based on what you calculate. So I interpreted, and still to this day, don't tell my dad, interpret that to mean if VC is limited, then all of those equations are limited to 5 square root of prime C BWD. Not the case, according to everybody else. That the VCI and the VCW, this requirement seems to be related more to just this equation. It shows up where this equation is written. So the world, except for me, has decided that that's the only equation that has an upper bound. And my argument is, when has the code, any code, ever had boundless extremes? It's ever allowed you to go to infinity if you did. I mean, and it's possible, you can see with some of these equations. The argument against that is that you use the smaller of the VCI or the VCW, and so one of those equations will limit the other equation from getting too large. It seems to work that way, but there's no specific upper limit to the VCI or the VCW, and you're allowed to use the smaller of those two. Seems strange to me. I've read a lot of code, seismic code. I've designed a lot of materials. And to the best of my knowledge, this would be the only time where equations are written that have no upper bound. So But because I got hammered so badly and my dad was not going to invite me to any holidays anymore, I've decided to change, and we now follow the herd. That the only equation that actually has an upper bound of 5 square root f prime c bwd will be that VCN equation. Yeah. Okay, some important points. VU and MU have specific definitions. And for us, if we're just looking at dead and live load, we're talking about whether or not it's V or it's M. It's 1.2 dead and 1.6 live. There is no secondary effects. The code specifically says that for the flexural capacity and design, you need to include secondary effects. No such thing is stated about shear. So again, the world has just ignored that. I'm okay with that because typically it's a pretty small portion. But by the way, you students, if I ask you what the shear component is of secondary effects, and this happened on a test once, don't come back and write to me, insignificant, I'm not doing this part of the test. That will not bode well for you. It didn't bode well for those students who tried that. Now, while the general practice has been to just not include secondary effects because they're relatively small in shear, doesn't mean I can't ask you a question about calculating those on an exam or anywhere else that I feel like it. So, okay, but VU and MU in these equations just based on the load factors with no secondary effects. Again, we're going to ignore VP. I told you I had an easier way to come up with VI and Mmax, and those had strange definitions because that's the way the test was run. Really what we're going to do is, for the most part, we can take any ratio of V and M that occur at the same location. In the project that I'm going to have you work on and the shear homework that you're going to work on, I think it's typically fair to use those as the live load shear and the live load moment, because that really is the majority of the load that's supposed to be applied after pre-stressing. You know, the concrete weight's already been baked in, so that's not included, and that's most of the dead load. The pre-stressing happens, and then it says loading after pre-stressing. So really, most of the load after pre-stressing, we're just talking about live load. Yeah, there's some additional dead load that goes in there. That's not going to be included. So I think if you will just take the shear and moment at live load, you'll be real close, if not exactly the same. And again, for the simply supported beams, you can take any shear and moment ratio. That ratio should be constant for any type of loading. So we'll do all of those things, and I'll try to explain it and make it clear. Code says got to have 40% of the total tensile strength provided by the pre-stressing. We're just going to assume that we do. We will. We always do. So that's it. One thing that has come to me from various students in the past is what I'm about to talk to you about. And I don't know how you learned shear design. You know, we had to do Moore's circle all together, and you know, that was fun to try to understand why loading due to gravity, and by the way, in this class, gravity will always be assumed to be acting down. Fair assumption. But why vertical loads actually create a 45-degree crack. You know, that was the old Moore's circle stuff. I will not claim to have really followed all that, but I know that the cracks happen at 45 degrees, so I buy that part of it. But so I've had students come to me and say that their instructors said that it would be absolutely best to provide shear reinforcement that went like this. That would be the superior way to provide shear reinforcement. Now, I fundamentally disagree with that. I want you to understand that, look at this picture, draw this picture, and for dramatic effect, I drew father and son standing below this beam. When this beam cracks, it's coming down. Again, we're assuming gravity acts down. When gravity acts down and this beam starts to fail in this direction, these stirrups are in direct tension. And we always want the rebar to be in direct tension. Always. Flexural reinforcement should be in direct tension. Shear reinforcement should be in direct tension. We don't want to kink steel. Now, I kind of exaggerated that in this picture, but that's when bars start to rupture. Rebar's not meant to bend. It's meant to be axial. So that's how it works best. And I want you to think about this and understand that that we're not making a mistake. It's not because it's easier to construct. This is what we want to see. This is how we want it to be. Another mistake I've seen students do, particularly on their project, is to start the stirrups. Now remember, I'm going to back up a second. Reinforced concrete says we can go out a distance D, as it's defined, and calculate VU at that location. So we only need to provide capacity for the demand at a distance D from the support. That's because this is assumed to be in a compressive strut, and it's going to get directly in to the column. So that portion of the load gets discounted for the shear design. Okay, makes sense. But what I've seen students do is then decide somehow, for some reason, that that's where the stirrups start. So they think we just start the stirrups at that point and start moving over. Remember this picture. This picture, if we didn't have stirrups in this section, we'd be in a lot of trouble. These two would be in real trouble. So don't confuse the fact that our demand is allowed to be taken out here. But we've got to provide capacity, and we start at 2 inches from the face of the column. That crack that's trying to develop, that needs all the stirrups going through it to hold up this beam. If there's none there, this beam just falls. So please keep that straight. Second thing is, we're not reinforced concrete, as they call it. We're post-tension concrete. We're pre-stressed concrete. Because D, remember D could be doing this, and D's doing all kinds of stuff, and D is never the same 2 locations, theoretically. So we don't use D in pre-stressed concrete. What the code uses is H, and instead of giving us the full H, they've decided that we have our demand is taken at H over 2. So in your project that you're going to work on, that's where your first check will be. That's where your demand capacity will be done. H over 2. Okay, we don't use D. Okay, I think I've beaten that stuff to death. Let's get to the example. See, I already did this entire video and Camtasia was on the wrong setting. So we're actually on take 2. Okay. So this is a precast beam. This is what this was intended for, these equations. This actually is supposed to make sense, and maybe it does. So 7 bonded tendons, though that doesn't make any difference to the shear. Bonded or unbonded, it doesn't change anything about what we're doing. I've given you all the section properties of the beam, and I made this a T-beam for a specific reason. We have to do the checks to the tension side when we're doing that effective cracking moment, and if it was just a rectangle, the section modulus to the top and the bottom would be the same, so you wouldn't learn the lesson that we're trying to get to the tension face. And in this example, the tension side is always the bottom. Simply supported beam. The tension side, due to applied loads, is always the bottom. And that's the way it reads. So due to the applied loads, we will have tension one end to the other on the bottom. So our section modulus to the bottom is going to actually be the section modulus tension. Okay. I've given you service loading. We're going to multiply that by 1.2 dead, 1.6 live. We will not include secondary effects, which there wouldn't be any on a simply supported beam anyway. And the question is, calculate the stirrups at h/2 from the face, either one, of the support. And we'll calculate first using VCN, then the minimum of VCI and VCW. And then for fun, just to show you that it is a lot of work to do all that, but we do get a benefit. If we just use this as a non-pre-stressed member, you're going to see that you have very tight stirrup spacing. So start with VCN. For the life of me, I don't know why I wrote all this stuff. It's kind of the obvious stuff, but bottom line is VVN's got to be greater than equal to VU. Okay. And the trick, all the work we're going to do is really right here, figuring out what VC is. So our first stab at VC will be to look at VCN. Okay, we went over that. I point out one more time that there's really nothing in this equation that has the slightest bit to do with the fact that this is a pre-stressed member. And I will back up and I will say one more time, please don't forget, this dP is the only D or dP in all these equations that does not have that 0.8 H limitation. So it's actually whatever dP is. As small as it gets, you got to use that. Was that a mistake? I don't know. D, on the other hand, is outside this. This does have a limit of 0.8 H. And particularly, when we get to the project, try to keep those straight. And that's going to be confusing. When you're using this equation, dP and D, and in your homework, can be different numbers, very different numbers. So 0.8 H in this case is 24 inches. So we'll keep that in our pocket. So we are at h/2 from the support. That's where we're going to start all of our calcs. So we need to know what the shear is. We need to know what the moment is at that location. Not the center line, not at the support, but everything that we're doing is happening at h/2 from the support. So I think you can follow this. I'm going to kind of go through this quickly, especially since this is the second time I'm going through this now. I'm starting to lose my voice. But calculate the moment here, and we start with the moment here and subtract out the area underneath the shear diagram. So that's what I'm doing here. And I come up with 150.2 foot kips, or 1802 inch kips. And remember that dP I calculated at h/2, and that's 10.4 inches. So it was 9.32 at the support. It's actually growing a little farther from the compression face as we got over to h/2. So that's really all we needed. We know we have 4,000 psi concrete, and we plug all that in, multiplied by, remember, this was dP, this is D. So not the same in this equation. In VCI and VCW, they will be the same. Okay. And for some unknown reason, this part of the equation must be less than 1. So we calculate that, VU dP over MU. It is less than 1. We cheer. We use that number. And we come along and add these up. 0.6 square root F prime C, 700 times all this other stuff. about 470 psi. We multiply those two by BWD and come up with 195 kips. But remember, according to my dad and everybody else except me, this is the only equation that has an upper bound of 5 square root f prime c. So we all agree it applies to this equation. We just don't agree if it should apply to the next ones. But that's 124. I, for some reason, decided not to run through those calculations. We don't know what I was thinking at that time, but it's probably something very deep and spiritual. So in actuality, we calculated 195 kips. And in your homework, I'm going to ask you to do this too. I want you to show me the calculated value, and then I want you to show me the limiting value if that actually controls. So 121.4 is actually our controlling value. It's the upper limit, 5 square root f prime c. So, okay, we've established VCN. We'll move over to VCI. Remember, we can use the smaller of these two. So this is the tough one. This is the one that's just not a lot of fun. Again, for some strange reason, the demand shear in dead load only actually affects the capacity of that section at the same point to resist load. Okay, so we're going to actually calculate that, and all I'm doing here is saying that the dead load only was 3.5 kips a foot. I'd already calculated MV and WU, so this is the factor loading. All I'm doing is ratioing the dead load to the total factor load multiplied by the dead load shear at that location, and I come up with just the dead load. I'm sorry, this was the factored shear. This is just the dead load shear at that location. Pretty simple stuff. Moving over to the effective cracking moment. We are trying to figure out when this will crack. And remember, this is the section modulus to the tension side, not the top necessarily. In fact, in this case, it's the bottom, but section modulus to the top, or to the tension side. So, Y bottom that I gave you in the beginning of this is 20.68. That's actually what this term is. So we're going to use Y bottom there. I'm sorry, we're going to use the section modulus to the bottom there. Y is this. So okay, FPE again. And I want you to kind of wake up, take a sip of coffee, maybe 2 sips, and follow this one, because this is going to come up later. FPE defined as the compressive stress due to pre-stressing only at the extreme fiber, where external loads cause tension. So external loads cause tension at the bottom, so we're looking at P over A plus M over S. So the question that can get complicated is, what's the M? The P over A is pretty straightforward. So we know we have 186.2 kips in pre-stressing. We have an area of beam of 880 square inches. In this case, because this is part I want you to wake up for, because this is a statically determinate beam, and you remember from the first homework assignments that this will always be, in a statically determinate member, the primary pre-stressing moment. Primary pre-stressing moment is the force times the eccentricity between the centroid of the member and the center of gravity of the pre-stressing. So that's what I'm doing here. I want to warn you, and I want you to put some notes in here somewhere. Some notes to yourself. When you get to the project, you can't do this. The project is a statically indeterminate beam. So you can't use the primary pre-stress moment. Hopefully by now you are a big fan of the fact that statically determinate members, when you put the equivalent loads on, will always create the primary pre-stressing moment diagram. When you put the equivalent loads on a statically indeterminate member, you don't get that. Remember, and the difference was the secondary effects. So This M equivalent in a statically indeterminate member for your project, you must use what you calculate in a moment distribution due to the equivalent loads at this location. You can't use this. This makes life easy, but it's not the way the code's written. So here, you're going to do F times E. In your homework, you're going to be able to do F times E because I'm giving you a statically determinate member there too. Just be careful. And in you UCLA students, I put this on the final, and I give you two choices. You get to calculate the equivalent moment in these equations. I give you enough information to make it the primary pre-stress moment, and I also give you enough information to choose the equivalent moment due to a moment distribution. That's the one you need to pick if they're different. If they're different, it's because it was statically indeterminate. So, okay, hopefully I've confused everybody enough with that. In this case, FPE, and these are additive because remember, we're on the tension side of the beam where tension is created by applied loads, but compression is created by the pre-stressing. So this compressive stress plus this compressive stress is what the code's looking for up here. Good. Now we've got to calculate the dead load stress through unfactored dead loads. Well, we'll need the dead load at h over 2. And again, I'm just going to do the same thing I did before. I'm going to use what the dead load kips per foot is divided by the factored kips per foot multiplied by the factored moment at that location and come up with just what the dead load moment is at h over 2. Dead load stress, pretty easy. Dead load moment divided by the section modulus to the bottom, because the bottom is where tension is created. Everything in this equation is looking at the bottom. We're trying to find the crack. So dead load stress at the bottom of the beam at h over 2 is 297 psi. So finally, we can put all this stuff together. This should be the same section modulus to the bottom. If it's not, don't let me know. 6 square root f prime c plus the FPE, that helps. We've got to overcome this to crack it. This helps even more, and this hurts us. The dead load stress is actually working against us. So 100.8 foot kips is the effective cracking moment that we think we have. Again, back in that equation, I've got to use VI over M max and multiply that by what we just found. In a simply supported beam, this is going to be a constant ratio regardless of what loads we're talking about. So I'm just going to use, because I already calculated it, I'm just going to use the dead load shear and the dead load moment and stick those in here. Not technically the definition, but it gives me the exact same answer. So good enough. So after all this, VCI is calculated as 0.6 square root f prime c BWD plus the dead load shear that nobody understands why that increases the capacity, plus this ratio times the cracking moment. All that comes to 158.3 kips. Very good. Now we're going to check the other equation. The only equation that I think really makes sense, I've said that. VP is going to be taken to 0. FPC is just F over A. That's 212 psi. That's going to end up going right here. So really as straightforward as it can get. We start with 3.5 square root f prime c. We add 30% of the direct compression multiplied by BWD, with the D's limited by 0.8H in this equation and in the VCI equation. And we get 109.4 kips. In summary, that first equation, even though this was limited to 5 square root f prime c, it's going to end up being the controlling factor, because If we look at these two, the smaller of these two is the best we're going to get to use, and that's 109.4 kips. But we got a better answer just using the VCN equation. So this will be what we use. The most efficient design will be used in this particular case using VCN. We will check the lower limits. The lower limit, 2 square root f prime c, is 48.6. Not a factor. So our phi VC value now is 0.75. Phi is always 0.75 for shear. Times the 121.4 is 91 kips. Okay, now we're home free. Now everything reverts back to what you already learned how to do. This is just reinforced concrete all over again. All that brain damage was to come up with the V sub c value that used to be 2 square root f prime c BWD when you learned in reinforced concrete how to design shear. We did all that extra work to get that VC, but now things are the same. So hopefully you approached, I assume you did, calculating VS required. We need 33.7 kips of shear due to the stirrups, shear capacity due to the steel. We're typically going to use number 3s. Now, in reality, on our drawings, we will actually call this D11 bars. D11, the 11 in that is actually the area of steel of a number 3 bar. A number 4 equivalent wire. This is called a wire. This is D11 wire. So if we specify D11 wire at some spacing, it's exactly the same as specifying number 3 stirrups. So a number 4 bar would be a D20 because a number 4 bar is 0.2 square inches of steel. So that's how this works. We're just going to talk about stirrups, but when you get out to practice, it's, I think, more common to look at the wire designation or to see that. So I'm going to rewrite everything in terms of the spacing. And we calculate needing 9.4 inches of spacing. 2 legs, number 3 stirrups, 9.4 inches of spacing. Now, after having hundreds of students, I would like to ask you to just leave that number the way it is so that I don't get depressed. Because the depressing part for me is watching you do all this work correctly, get to the very end, and decide to round that number up to 10 or up to 12. Because somehow, some way, you think a larger number is giving you more capacity. A larger spacing is giving you less capacity. So if you're going to round, round down. The answer is either 9 or 8. Do not round up. And the safest way not to expose yourself for not being taught well enough is just to leave the number where it is. So that's fine by me. That applies to the homework assignment and the project. I don't care. I understand that when you get out to work, you're not going to use a 9.4 spacing. Your office will have you round that to 9 or 8 or something like that. But for what we're doing, for my mental health, I'd like to just see you leave it. Or round down. So what is the spacing, largest spacing we can use? It's the smaller of 0.75H or 24 inches. So in our case, with a 30-inch deep beam, 0.75 of H is 22.5 inches. So what that says is, regardless of what you calculated here, you cannot put in a spacing larger than 22.5 inches. Now be careful, particularly UCLA students. I like on the final to ask, what's the largest spacing allowed by code? And I give you a situation where you have to calculate, you end up calculating this. And I have too many students every year tell me, but the largest spacing we're allowed at that location is 22.5. No, that's not the right answer. The code won't let you kill people. It's very much against that. The largest spacing that the code will allow is either what you need for strength or the absolute maximum spacing. But in this case, and on the final, that's the answer. You can't satisfy code and put a spacing in larger than 9.4, or you violate the code. So, for those of you who made it that far in this video, you're going to have, and you're at UCLA, you're going to benefit. Okay, I'm going to go through this quickly because there are two other equations in here that I'm convinced, more than one person, more than one university ends up doing work for anything. Testing. They're doing some testing. We're doing some testing. Everybody's doing some testing, and everybody wants their testing reflected in the code. Well, somebody's testing came up with these as minimum steel. Now, I have done every example I can come up with. Normal examples, examples that make sense, examples that don't make sense. And I can never find a case where these equations govern the minimum steel or create a maximum spacing that's less than the maximum spacing that we just talked about. And I'm just convinced they must have popped out of somebody else's testing that needed to be represented in the code. Because one of the strange things about these is what the code says is you get to use the smaller of these two AV minimums. When does the code ever do that? You check two equations, you get to use the least conservative of the two. That's what the code says. So I will quickly do that here just to show you that one of the equations gives a number that actually might make sense. But the other equation gives 71.5 inches of spacing. And these have been rewritten. So, the minimum AV becomes the maximum spacing in these equations if you rewrite for spacing. So that should make sense. In this particular case, 71.5 is a much larger spacing, maximum spacing, than the 22.5 that we already had. So it was a waste of time to do this calculation, and it is always a waste of time to do these calculations. So we're not going to do them in this class. We're just going to ignore these equations. And I dare you to find any time that those equations actually control. You can just take my word for it. Now quickly, let's say we just didn't like all these equations. We didn't like them, we didn't trust them, they gave us a headache. We just wanted to go by 2 square root f prime c. Well, you've done this before, so you don't need me to walk you through this. But in that case, if we just looked at this as a reinforced concrete beam, we'd have to space 2 legs, number 3 stirrups at 3.9 inches. That's pretty darn tight spacing. We don't want to do that. It's about almost a third of what the spacing we're actually going to use for this beam. So there is tremendous benefit by post-tensioning, by pre-stressing. There's no question about it. You just got to do a lot of work to get those benefits. Okay, I want to point out, for those of you who made it this far, I have come up with an example that's very much like your homework assignment. And if you notice that, and you decide to walk yourself through, you're going to see that I've effectively shown you step by step what to do in your homework. This is different, and this, you'll get strange results, and after doing all the work, you won't trust them, I hope, and that's the point, because we're going to actually have an inflection point here. We're going to actually have negative moments and positive moments. This isn't the way those equations were developed. And all I have to do is stick on a cantilever, still make a beam statically determinate, and you'll see these equations go haywire. So that's what's going to happen. I do this every year. I don't care what year we're in, you're going to get a homework assignment. You're going to do a lot of work. I've taken my foot off the gas, by the way. I used to make the students, I'd give 5 points, 5 locations along the beam. 3 of those could be computer generated, but they'd have to write their own computer software to calculate the VCN, VCI, and VCW. And then I wanted 2 locations done by hand. It was time intensive. It was not fun for anybody. And I've decided in my old age to just have you do 2 locations by hand. Maybe I'm getting nicer, maybe I'm getting lazier. It's hard to decide. Maybe I'm getting grouchier. I don't know. The latter is probably the case. But anyway, that's all I'm having you do because I got to grade this stuff too. But if you go through this, you'll see what I want you to do. Just follow this example. Again, I wish there was some epiphany you were going to have, some deep meaning. You're not. You're not going to find any of that. You're just going to have to know how to do this. And as much as I hate all this shear stuff, I still want anybody taking my class to be the best at it. So even the miserable stuff, you're still going to be the best. So you'll go through this as I have. You know, I did the VCNs at all the locations. I did the VCI at all the locations. VCW. And all those locations mean the things change when you have negative moment versus positive moment. So the D's are then measured from the opposite face. You can see where the complications come in, and that's why I'm having you do multiple locations. You're also going to see strange results. So when all this is said and done and you design the stirrups, you're going to come up with something that looks like this. And where you expect to have the tightest stirrup spacing, you likely won't. And you won't, because I'm not going to give you a problem like that. As you get away from the maximum shear and decrease the shear substantially, you're actually going to need more stirrups. Doesn't make any sense. Again, same thing coming from the other direction. You're approaching a zero shear somewhere in this range, but you need more stirrups. And when you get back to where you'd expect to have the tightest stirrup spacing, they start spreading out again. And honestly, the point of this homework assignment is to make you not trust this very much. What I can say is the proof's in the pudding that these equations seem to give conservative results because there are no failures in shear that I'm aware of. By following these with the proper loading, these don't fail. So the equations work, but you get strange answers. And that's the part that, it's kind of hard to trust. So I've got a little summary sheet if you want to go buy it. Pretty simple stuff. Phi factor, remembering that VVN has to be greater than VU. What the VC calculations are, you have 3 equations to go through. You have a lower limit that we're going to use of 2 square root F prime C, and we're going to use a 5 square root F prime C for the VCN equation only because we're following the herd. These are your equations that you learned in reinforced concrete for calculating the stirrup spacing. And then we have maximum spacings. And for us, we're always going to be in this range. I don't want to complicate things, but we're going to assume that our VS demand is less than 4 square root F prime C BWD, and that will establish our minimums. And there is a VS max, and I tend not to check that because I'm lazy. And at the end of this, if you want, you can ask me for this article that we wrote for Concrete International, my dad and I. Some father-sons go to baseball games, some go fishing, and some write articles on shear nonsense. So that's what we do. To each his own, And we try to explain, basically doing what you're going to do, that a change needs to be made. Now, we got to the end of it, and people read it, and they said, wow, great stuff, really good stuff, really liked it. And absolutely nothing happened after that. No, not entirely true. Like I said, there was some infighting, different opinions. Actually, they were going to make it more complicated, which is the worst thing possible. And then it just got all dropped. So that's where we are right now. Anyway, that's it for shear design. Thank you for listening, and good luck on your homework.